Quantum computing is something a lot of people have some conceptual understanding of. But often, when people hear the word quantum, they think that the math is just too complicated. This video series will try to give at least some basic understanding of quantum computing, but from a mathematical standpoint. Only some basic knowledge of linear algebra and vector analysis is required. Let's get into it. Imagine we have a plane, where the x and y axis are replaced by 0 and 1. We can define a vector, say, with components -2 and -1. Let's label this vector as the Greek letter psi, with the respective coefficients in front of 0 and 1. These coefficients are actually complex in nature, but that doesn't really matter right now. The point is that these coefficients can be any number, allowing us to define vectors of any length in any direction on this plane. Psi becomes what's known as a linear combination of 0 and 1. This is what's called a vector space that's spanned by 0 and 1. The values 0 and 1 form the computational basis. And because these vectors have a basis, we can do things like apply transformations on them, which we'll define in future videos as quantum gates. The actual fundamentals of psi are what's known as the state vector. These vectors are actually representations of quantum bits, or qubits. State vectors exist as superpositions of 0 and 1, and only upon observing them, they collapse into either 0 or 1. The probability of realizing 0 when examining the qubit is alpha squared, or the coefficient in front of 0 squared, and likewise for 1. Therefore, the sums of these coefficients squared that define the state vector must add to 1, as the probability has the total to 1. Once a qubit does choose whether to be a 0 or 1 after observation, it stays as a 0 and 1. No one knows why this collapse occurs in the first place, we simply have to take it for what it is. Say we have a qubit floating in space. It can exist as any vector and undergo any transformations so long as it satisfies the probability equation. Let's isolate one. We'll see later that this qubit is defined by the following state vector. If we square the coefficients, we'll see that half the time, once observed, the qubit will collapse to 0. And half the time, it will collapse to 1. Because the square of the coefficients equal 1, it's similar to the trigonality stating that sine squared plus cosine squared equals 1. If we do some math, we can get this funky equation that's a function of the variable gamma, theta, and phi, but we'll see in later videos that this gamma function at the beginning is pretty much useless, so we just end up with a function of theta and phi. For those of you who know spherical coordinates, using theta and phi we can define spherical coordinates where 0 and 1 are the poles. Theta defines moving along the xy plane, and phi would define moving up or down towards the z-axis. We can visualize any qubit along the sphere, and this visualization of a single qubit is known as the Bloch sphere. Suppose we have two qubits. If they were classical, we'd have the following combinations: 0, 0, 0, 1, 1, 0, and 1, 1. A two-qubit system has 4 computational basis states, denoted as the same. However, the new state vector is defined with coefficients for every combination of the qubits. As a result, each of these coefficients squared must equal 1. This implies that no matter the dimensions of the state vector, its norm must always be 1, and this is known as the normalization condition. Going back to the two-qubit system, if we try to determine the state of one of the qubits, The probability that we get 0 is determined by adding the squares of the coefficients with the first index of 0. After the state vector collapses, it must be divided by the renormalization factor in order to maintain a norm of 1. There are no easy visualizations of multi-qubit systems, but I'll do my best to give an idea. Imagine we have 3 axes, with the fourth basis state being defined by the changing color of the vectors. If we measure the state vector and it gives 0 for the first qubit, the state vector collapses into a plane spanned by 0, 0, and 0, 1. The state vector afterwards also has to shrink down to a magnitude of 1 in order to satisfy the normalization condition. You might be asking yourself, how can we even do any computations with qubits? We don't know what values or information even exist until we make an observation. This takes us to the EPR paradox, a concept posed by Einstein, Podolsky, and Rosen in 1935 as an attempt to point out a flaw in quantum mechanics. Suppose we have the following 2-qubit system with only 2 coefficients, alpha 0, 0 and alpha 1, 1, each being 1 over the square root of 2. If we square the coefficients, we get a 1/2 probability for both 0, 0 and 1, 1. This means that if we try to observe what the state vector is, half the time it collapses into 0, 0, and half the time it collapses into 1, 1. And since the qubits are the same in each final state, observing the second qubit would yield the exact same result as the first one. This would mean that sometimes the state of a qubit isn't unknown. If we measure the first qubit, instantaneously we would know the output of the second qubit as well, no matter how far apart these 2 qubits are. But how is this possible? The answer is quantum entanglement. If we had 2 entangled qubits, any distance apart, the second we measure 1 qubit and it collapses. The other one ultimately collapses as well into a known value. This was proof that information can actually be stored in qubits, and ultimately proof that quantum computing was possible. This video is an introduction to the math behind quantum computing. In the next few videos, we'll actually be going into performing computations with qubits, so stay tuned. Thanks for watching.